All right, let's dive into this. Have you ever had a moment where reality just felt, well, a little bit off? Like a glitch? Today, we're going on a wild journey into one of the most mind-bending yet surprisingly rigorous scientific mysteries of our time. We are breaking down the simulation hypothesis. It's literally the ultimate question, isn't it? Are we living in a computer simulation? I really want you to challenge your basic perception of reality for a second here. What if the universe as we know it, every galaxy, every star, every single person walking around, is actually a highly advanced artificial construct?
There's this incredibly provocative thought at the core of all this. Everything you've ever touched, seen, or felt could be fake. Now, a couple of decades ago, that kind of talk was strictly reserved for late-night college philosophy debates or sci-fi movies, right? But today, it has totally transitioned into serious academic discourse among top-tier theoretical physicists, cosmologists, and information theorists. And that's exactly why we need to unpack the actual hard science behind the fiction.
To understand how we got here, here is our roadmap for this explainer. 1. The simulation trilemma. 2. The universe's source code. 3. Conditional rendering and reality. 4. Searching for the grid. 5. The mass of information. 6. The quantum roadblock. We're going to take this step by step, going straight from philosophy to hard data. Section 1. The simulation trilemma. So this whole modern debate formally kicked off in 2003 with Oxford philosopher Nick Bostrom. And what's so compelling about Bostrom's logic is that he didn't just throw out a wild guess. He actually presented a very strict statistical trilemma. He basically argued that based on our current trajectory with technology, at least one of these 3 steps absolutely must be true. Step 1, humanity goes extinct before reaching a super advanced post-human stage. Step 2, if we do somehow reach that stage, those post-humans are highly unlikely to run simulations of their own evolutionary history. Or, Step 3, we are almost certainly living in a computer simulation right now. Bostrom's framework is an absolute game changer because, well, if you believe human civilization will survive and just keep advancing our computing power, Step 3 actually becomes the most logical statistical conclusion.
Section 2. The universe's source code.
So how do we actually take that philosophical idea and apply it to information physics? Well, think about how we might translate physical laws into a giant operating system. In a computer, you have a maximum processing bandwidth. In our physical reality, we have the speed of light, an absolute unbreakable limit on how fast information can travel. A computer monitor has a strict pixel resolution limit, right? Well, our universe has the Planck scale, the absolute smallest measurable unit of space and time. Beyond the Planck length, the math of general relativity literally just breaks down. It's perfectly analogous to zooming in on a digital photo until you hit the individual pixels. It's kind of crazy to think about.
Section 3. Conditional rendering and reality. Okay, so you might be wondering, how could a cosmic scale simulation actually function without instantly crashing the system from sheer information overload? I mean, that's a lot of data. The answer might actually lie in what's called conditional rendering. In modern video games, to save massive amounts of processing power, the environment is only fully rendered when your character is actually looking at it. And here's the wild part. This perfectly mirrors something we already see in quantum mechanics called the observer effect. In the famous double-slit experiment, subatomic particles behave as a wavy cloud of probabilities until they are actively observed or measured. At that exact moment of observation, their wave function collapses into a definite physical particle state. So, is wave function collapse just the universe's physics engine rendering a specific outcome only when a player or observer queries the system?
Section 4. Searching for the grid. Now this is where we shift from really cool theory to hard empirical data, because real physicists are actively searching for physical glitches in the matrix. Let's talk about the Greisen-Zatsepin-Kuzmin, or GZK, limit. Simply put, cosmic rays traveling across space eventually hit this hard energy speed limit at around 5 × 10 to the 19 electron volts. Now, standard astrophysics explains this through radiation interacting with the cosmic microwave background, but physicists have actually demonstrated that an underlying computational simulation grid would mathematically enforce this exact same hard speed limit.
Building on that exact idea, researchers like Silas Bean proposed that if spacetime is actually a discrete grid, like a lattice, ultra-high-energy cosmic rays shouldn't travel perfectly evenly from all directions. They would travel preferentially along the geometric lines of that grid, showing a directional dependence, which is known as anisotropy. Observatories like IceCube and Pierre Auger are crunching the data right now, actively hunting for these lattice signatures. But, and this is a big but, just maintaining total scientific objectivity here, no definitive grid signature has been confirmed yet. The hunt is very much still on.
Section 5. The mass of information.
Let's pivot to some truly mind-bending research from Dr. Melvin Vopson on the mass energy information equivalence principle. Think about this incredibly tiny number, 3.19 times 10 to the negative 38 kilograms. By extrapolating from established physics, Vopson formulated that a single bit of digital information at room temperature actually has a tiny but real physical mass at roughly that exact value. I know, it's microscopic, but it implies something absolutely monumental. Information itself might literally be the fifth state of matter.
And when we scale that up, we hit this unbelievably massive number, 6 times 10 to the 80th power bits. That is the estimated total amount of information in the entire observable universe. But wait, it gets even more fascinating. Vopson proposed the second law of information dynamics. He discovered that unlike physical entropy, which basically always increases to create disorder and chaos, information entropy tends to decrease, or at least remain constant over time. Basically, natural systems, whether it's genetic mutations or digital data, naturally self-compress their information content. Just like an optimized computer algorithm trying to save hard drive space. How cool is that? Section 6. The quantum roadblock. All right, it is time to ground all this soaring speculation with some cold, hard reality. Simulating just a few hundred quantum particles requires more memory than there are atoms in the observable universe. Let that sink in. In 2017, physicists Zohar Ringel and Dmitry Koverjin proved mathematically that the computational resources required to simulate quantum entanglement grow exponentially. Because of this extreme quantum complexity, it is functionally impossible to simulate our universe on any classical computer architecture we can conceive of. And that reality check leads us to the biggest scientific critique of this whole thing, the falsifiability problem. According to the established philosophy of science, a valid hypothesis actually has to be falsifiable, meaning there has to be a way to prove it false. But if we're inside a simulation run by infinitely powerful beings, well, they could simply manipulate our scientific instruments or even our memories to hide any glitches. It fundamentally demands an immensely powerful quantum computing architecture that is currently entirely beyond human understanding, which kind of makes the hypothesis, at least for now, untestable.
So let's bring this all together with our key takeaways. The simulation hypothesis is so fascinating because it translates our known physical laws directly into information processing frameworks. It allows us to view computational limits, like the speed of light and the Planck scale, in an entirely new structural context. Now, for sure, it remains absolutely unproven. But honestly, regardless of whether we're made of digital code or biological carbon, the sheer pursuit of this hypothesis is spectacularly pushing the absolute boundaries of empirical physics and human computation.
Which leaves us with one final, deeply provocative question. If discovering the underlying truth of our universe eventually proves we are, in fact, simulated, does that make our reality any less real? I mean, if your pain, your joy, and all our greatest scientific discoveries are just coded, do they matter any less? It's a profound thought that completely blurs the line between hard physics and deep philosophy. I hope this explainer sparked your curiosity and helps you look at the universe through an entirely new lens. Keep questioning everything, and I'll catch you in the next explainer.